Hello everyone, welcome to this lecture number 13 of NPTEL lecture series on charging infrastructure. In this particular lecture, we will talk about closed loop control of single phase boost PFC converter, and in previous 2-3 lectures we were discussing about how one can size and one can decide on this sizing of different components and can select components with required ratings and thus can able to physically realize this single phase boost PFC converter in hardware. So, over these 2-3 lectures we have derived some of the important aspect. First we have seen we have derived the duty ratio, which is nothing but the fraction of the time of switching period during which this switch S1 is on. That we come to conclusion that is nothing but 1 minus modulus V s sin omega t by V naught. And then similarly we have also calculated the inductance value, which is nothing but V naught by 4 delta L max times f switching frequency. Similarly we have also defined or calculated the capacitance value, and we have also seen that this capacitance also has the second line harmonic frequency component in the voltage, in the capacitor voltage which it is there. So, this second line harmonic component is one of the reason why the capacitance size is enormously very high, and this is one of the problems in single phase AC to DC converter, where the converter is operated in such a manner that the unity power factor current is drawn and it is maintaining a fixed output voltage V naught. So, this second line harmonic component or the second line harmonic frequency component is one of the important consideration which will be there onto this capacitance. Then we went ahead and derived the RMS current expressions for S1 switch. We have also derived RMS current expression for S2 switch. We have also derived the average current which will be flowing through the S2 switch. Similarly, one can also derive the average current which will be flowing through this S1 switch, nothing but I average S1 1 by T by 2 0 to T by 2 S of T D of T. So, easily one can also calculate the average current through S1 as well. We have also seen the voltage ratings of S1 and S2 is nothing but V naught, and generally one has to give certain safety margin, generally 1.4 times of that voltage which it has to block whenever the converter is in operation. So, the voltage blocking of these devices we have seen. So, accordingly depending upon the voltage rating and the RMS or average current rating, one can choose the appropriate devices which can be used to realize this S1 and S2 switches. Then we have also seen the RMS current through the inductor, which we obtain as Is peak by under root 2, where Is peak one can easily calculate using the formula defined. It is assuming that the converter is operating in such a manner that the unity power factor current is being drawn from the AC input source. And going ahead, we have also seen the RMS current which will be flowing through the capacitor is nothing but the under root the RMS current of this I converter current minus square of average current will be flowing through this load. We have also seen the some of the rating of these diodes. For selecting this diode, we have seen that for D1, D2, D3 and D4, the VRRM was nothing but Vs peak. The average forward current we have also seen was nothing but Is peak by pi. We have also seen the IRMS was nothing but Is peak by 2. So, using these ratings one can also select or one can also choose required diode, and thus one can easily realize this part of the converter, and using the formula we have derived one can also realize the other components, key components of this power converter. Now, up till now we have studied the operation of this converter, we have understood how one can size different component of this converter. Now the next important part is the closed loop control. Now if we see the in closed loop control, so what are the control objectives we are trying to solve in this particular converter? Using this particular converter, what are the control objectives? So the control objectives are, the first objective is obviously regulating the output voltage at a desired level or at value which is needed for basically to satisfy the specification of this particular stage of the power converter. So the first control objective is the regulation or controlling of output DC voltage at its desired value, now, and we have seen that fundamentally that desired value has to be greater than Vs peak. So if the specification is given as the output voltage need to be maintained at 400, then the closed loop control or the switches has to be controlled in such a manner that you will obtain that 400 volt whatever is the required or the desired value one need to have. The second control objective is, along with maintaining or regulating the output voltage, another important thing which is the most critical part for this single phase boost PFC converter is the unity power factor current drawn from the source. So thus the second control objective, whatever the things you are controlling, you must make sure that the unity power factor current is being drawn from the input AC source or from the grid, you can say. It is after the voltage control, this is second most important requirement of the operation of this converter. Now how you can maintain these two things? See, one cannot change this diode conduction period. It depends upon whenever it is forward bias it will be conducted, whenever it is reverse bias it will not be in conduction. So thus we do not have control, we do not have any control when the diodes are turning on and turning off. So this we do not have control. Thus L and C are the passive component which are being used. Now the only thing which are available with us which can be controlled are the switching time of this switch S1 and S2 within a switching period. So the only control variable or we can say the things one can change are the fraction of the time during which this S1 switch and S2 switch is on in a switching period. That means in how much time, for how much time this switch has to be on and how much time this switch has to be on in the TS period, when where TS is nothing but 1 by FSW, where FSW is very much greater than our line frequency. Generally this FSW will be in tens of kilohertz, maybe 10, 20, 30, 60, 70, depends upon the designer's choice. So that is the only thing you can control, which is nothing but the switching time for that particular switch S1 and S2, because if we control these voltages, then on an average sense we can control the voltages which are applied over here, and that is when you can make sure the current drawn is of unity power factor, and accordingly we can also control the output voltage one can obtain. So that is why we have this one particular thing is the duty ratio which has to be changed through the closed loop control. Here one assumption is been taken that the switching frequency of half bridge, that means FSW, is kept constant, because if we have varying switching frequency then it will lead to several other problems like EMIs, different harmonics appear in the supply current, operation of converter is completely different, and the relationships what we have obtained will not hold true. So, that is why F switching frequency is kept constant, which is at a very much higher value than Fs, which is nothing but the line frequency. So, now to obtain this to control objective, there are several control schemes which are being followed, and one of the commonly used control scheme is to control the average, is to have the average current control, which is nothing but which controls the average inductor current by appropriately changing the duty ratio of the switches. So, let us see how our overall closed loop control will look like. So, our first requirement is to maintain the constant output voltage or to have the regulated output voltage, and that particular output voltage should be at the desired value. So, we can define the reference voltage, which is V naught reference voltage, that what voltage one need to have or need to regulate at the output load. Now, that will be nothing but will be compared with the V naught feedback. Now, we will see how one can generate this V naught feedback. So, that will be generated using by sensing this particular V naught. So, we have V naught reference and which will be compared with the V naught feedback, and that will be sent to the controller, which is nothing but the voltage controller. One can use any kind of controller, it could be PI controller, it could be P controller, it could be proportional controller or proportional integer controller or type 2, type 0, some high order controllers also can be used. So, this is that particular controller. We will also see some of the guideline which can be followed to select this controller in subsequent lectures. So, then the output of voltage controller is sent to the saturation block. Now, let us understand why we need this saturation block. Now, if we see in this particular arrangement, what we have is we have the reference voltage which is been defined or which we need to maintain at its output. Now, we are also comparing it with the feedback. Now, if there is a difference in this quantity, for example, if this is kept at 400 and this is at 350 volt, then what it indicates that capacitor need to get charged up. So, the current drawn by the capacitor need to be increased such that this capacitor voltage will rise and will reach to this V naught reference value. And how one can make sure the capacitor will get charged more? One can make sure that capacitor will get more charge by increasing this I converter current. And how one can make sure this I converter current will get increased? This can be increased by ensuring that more current is being drawn from the source, because one cannot change the source voltage, one can only change the amount of current which can be drawn from the source. So, that means if there is a difference between the required or the reference voltage and the feedback voltage or the actual voltage, then that particular thing will give the indication that whether we have to draw more current from the source or less current from the source. Now, let us take one more example. For example, if you want to keep this V naught reference at 400 volt and let us say V naught feedback is at 420 volt, that means one need to make sure that this capacitor should discharge more and reach to that 400 volt mark. Now, to do that, one need to make sure the energy which is used to charge the capacitor should get reduced, then only we can make sure the capacitor will be discharging more, and that is when the voltage will fall down to 400 volt. So, that means how one can make sure it will be discharged more? By making sure this I converter value goes down. And how one can make sure this I converter value goes down? When this reduction in I converter is getting reflected in this Is current. And how one makes sure this reduction is in current can be ensured? By somehow making sure that there is a reduction in this IL current. So, there are two things. If my V naught feedback is greater than V naught reference, that means the capacitor needs to discharge And how one can make sure capacitor is discharged? By making sure the I converter get reduced, because this current which is going into the load one cannot control. So, one way is to make sure I converter get reduced, and how one can make sure I converter is reduced? By making sure the IL got reduced, and once the IL is reduced, it indicates that my IS will get reduced. Similarly, if the V feedback is smaller than V naught reference, that means the value at which you want to keep the voltage. So, in that case the capacitor need to charge, which indicates that the I converter need to increase, that indicates my IL need to be increased, and that indicates that my IS current which is being drawn from the source need to increase. So, what we saw that the difference of this voltages will actually determine magnitude of inductor current in the converter, because that only you can control by controlling the switches, and once this will get reflected here, you will see that that reflection will also be there on the IS current. So, now this will define my magnitude of that IL average current. Now, that particular thing I will multiply it with modulus of unit sine function, or you can say sine omega t, modulus of sine omega t, and that will give you nothing but IL or IL reference, that will give you the IL reference. Obviously, this will be in the average sense, IL average reference I should say, IL average reference, that averaging is done in a switching cycle. Now, this IL reference will be then compared with IL feedback. So, this defines the magnitude, and that will be multiplied with the modulus of unit sine omega t. That means, now this variation, if you look at this variation, so this particular variation, this reference variation will be of the form something like this, and the peak is nothing but defined by this. If I define this as IL peak, this IL peak, then this will be nothing but my IL peak, determined by IL peak, because this thing is now get multiplied with modulus of unit sine omega t. And now, this to generate this modulus of unit sine omega t, there are single phase PLL which are available, or one can also sense the grid voltage and then take the modulus of that, do the mathematical operation of that on that, and then remove the peak value, or to obtain the modulus of just sine omega t, and that one can multiply it with this output of the voltage controller. Now, why this saturation is given? Because once you have decised this particular converter, you know that what could be the RMS value of IS1, what could be the RMS value of IS2, what could be the RMS value of current of inductor, capacitor, diodes one can have, and that is when this saturated value or this saturation limit will be determined, because you have already selected the components. So, we need to respect the maximum current ratings of these components, and that is when that saturation is needed. So, one makes sure that this controller is tuned or is having such parameters such that control is happening and it is not going and getting saturated. So, one can do that exercise while defining the control parameters. So, let us see further. Let us again go ahead and see the further things. Now, after this IL average reference and feedback, so this again this reference and feedback, now again this will be having one current controller whose work is to make sure that this feedback will be following the reference, and then this current controller, sorry, this is the current controller. Now, if there is a difference between them, then this controller will make sure the error goes to 0, I mean this error goes to 0. And how one can make sure this error goes to 0? By making sure this, the duty ratio of these switches S1 and S2 is changed accordingly. So now this will be, obviously there will be some gain, we will discuss this gain as we go on. So there will be some gain which will actually convert this output into the duty ratios which is required. So that will define the duty ratio. Let me define that is a duty ratio in terms of S, and that will go to again the modulator block, and that will define my PWM of S1 switch, and one can take the NOT of that and can define the PWM of S2 switch. You can say this PWM is going to the gate driver of S1 switch, and this PWM S2 is going into the gate driver of S2 switch accordingly. Now one need to use the output voltage sensor. So this one can put the voltage sensor, and this voltage can be sensed and can be feed back to the voltage feedback, and then this controller will make sure the error over here goes to 0. And then this IL feedback, one can put the current sensor here and then take the current sensor feedback and connect to this feedback, and then this controller will be making sure that this error which is coming over here is making down to 0. Now if you look very carefully, here we are trying to control the average current which is going through the inductor. That is why it is also called as a average current control of boost PFC converter. We are controlling the average current which is actually following the modulus of sin omega t pattern. So that is why we have multiplied with the modulus of sin omega t. Now if we see here, this particular part is actually be placed inside the controller. This all things will be kept inside the controller. So this is the kept inside the microcontroller in the digital domain. One can design and kept it inside the modern day microcontrollers one can keep, and one can write down the particular codes for individual blocks, and that is when one can ensure the PWM S1 and S2 is coming out of this controller and going into the gate driver of these switches. Now here it is not D of S, it will be D which is going into the modulator. Sorry for that. Now let us see how we can design these controllers. And to design these controllers, one need to also know what will be the transfer function of the plant which you are trying to control, because once you know the transfer function of the plant, then only you can be in a position to define the controller parameters so that the response of the plant will be following your desired specification. So let us see how one can write down the closed loop control in the form such that we can easily able to analyze. So let us write down again the closed loop control. So it is nothing but V0 reference, the feedback will be coming over here, then you have a voltage controller, that will be going to via a saturation block, will be going to multiplier, and then that will define the, let us say, V0 reference of S, and the output of multiplier will be defined as IL reference of S, and that will be compared with IL feedback. Here it will be compared with V0 feedback, and that will be given to current controller, and the output of current controller will be sent to the gain Ki, which we have taken one gain, because this gain will be used to convert this particular controller value into the required duty, and that will define the D of S. Since we are writing down in the S domain, we are writing down this system in such a manner that we can use certain control system tools to select these controllers. So, that is why we are defining these parameters, or you can say this particular quantities in the S domain. So, this is a D of S which we are getting. Now, what it indicates that whenever there is a change in the duty ratio, that duty ratio, so if we see in this particular converter, whenever there is a sudden change in the duty ratio of switch S1, then the average value of V converter, which is V changes suddenly. This will result in the sudden change in the voltage across the inductor, and as we know that the current through the inductor will take some time to respond to the sudden change in the voltages applied across it. So, thus the dynamics of this delay in responding to the sudden change in the applied voltages need to be captured in a transfer function, and that will be the plant transfer function, which will actually capture the way that this particular converter behave once there is a change in the duty ratio. So, we will define a function called Gi of S. Now, this Gi of S is nothing but IL of S whenever there is a change in the duty ratio. We can define this as small IL, because that's a nomenclature which we are trying to follow. So, that IL of S upon D of S, that means whenever there is a change in the duty ratio, how that particular change in the duty ratio will get actually propagated, or you can say that how the system will get response to that change in the duty ratio. That means the current through the inductor, which will take some time, or it will have some dynamics to that sudden change in the duty ratio. So, that will be captured, that way it will behave, it will be captured in that Gi of S. Now, that will give you nothing but IL of S, that will be taken feedback to this, and it will be compared with IL reference, and this output of this, if you see this one, if there is a change in the inductor current, then definitely there will be change in the I converter current, and thus there will be change in the current which will flow into the capacitor, which will actually lead to the change in the capacitor voltage, which the capacitor takes some time to respond to that change, and that particular behavior or response of that particular capacitor will be captured in the transfer function. We define it as a GV of S, and the output will be nothing but your V naught of S, which will be again feedback into your system, where GV of S we can write the output of V naught of S divided by IL of S, and we know that whatever the V naught of S is there is nothing but same as that of Vc of S. So, what we are trying to do, we are trying to see whenever there is a change in the duty ratio, how the inductor current will respond to the change in the duty ratio. That information is been captured in Gi of S, and then once the inductor current gets changed, how the capacitor voltage will respond to that change in the inductor current, because the change in the inductor current will reflected in the I converter current, and that will actually be reflected in the current which will be going through the capacitor, and that will be actually be reflecting in the voltage of the capacitors, and the capacitor resists to that change, and that takes some time or have some dynamics involved in while changing the voltage of the capacitor. So, thus we will capture that dynamics in that particular GV of S. So, now our prime objective while doing the closed loop control, in order to understand the parameter of this current control and voltage control, our prime objective is to make sure that we know this GIS of S, which is how the inductor current will respond to the duty ratio change, that we should know, and with the change in the inductor current, how the capacitor voltage will respond to that particular change in the inductor current, that we should know. So, for that transfer functions GI of s and GV of s need to be known, which can be obtained using the small signal modeling, and while doing small signal modeling we will follow certain procedures to obtain the small signal model. So, the small signal model, so while deriving this small signal model we will first derive the average large signal model. Obviously using different state equations. Then we will give a small perturbation to the inputs such as duty ratio, input voltages, and then see the response of inductor currents, capacitor voltages towards these small perturbations to capture the dynamics. And then we will linearize the state equations around the steady state point, around the steady or around the operating point, and this linearization we will do by taking certain approximations, and once we linearize it around the operating point we can then convert the time domain equation into the S domain equations or Laplace domain equation or frequency domain equations, and that is when we get that transfer function of GI of S and GV of S. This we will derive in the subsequent lectures, and thank you for patiently listening to this lecture in which we have seen how one can do the average current control of single phase boost PSC converter. Thank you.